Hello. In this video, we will cover the run modes in GPX using the GPX library project. To open this project, go to the dashboard view and click on the icon next to select to open an existing project. In this case, I already have the GPX library project opened, as you can see on the right-hand side of the GUI, where it displays the project name, and also you can see that all the views are enabled. Before we do our exercise, we will save a copy of this project. To do so, click on the icon next to Save As and leave the copy selected from the Save As dropdown. We will name this project GPX Library Copy. You can click on Browse to select where to save this project, and I will save this on my desktop. I'll create a new folder and call it Library Copy. And then you can click on Select Folder. After doing that, click on Save to save a copy of this project. A pop-up message will appear asking you to make sure that any changes that have been made in the current project have been saved. And you can click Yes on this message. An information message will appear in the Messages Center, letting you know that the GPX library was successfully copied to GPX Library Copy. Click Done to clear the message. We will now move through the views to see the data that has already been entered in this project. Moving to the Observed Data view, we see that 3 different types of exposure data entries have been already created, as well as solubility data has already been created for some of the compounds in this project. Moving to the Compounds view, we see that there are 9 different compounds in this project. You can review the physicochemical properties of any of these compounds by clicking on it and then opening panels to analyze the properties of the compound. We'll skip over to the Simulations view. And from the Simulations dropdown, we can see that there are 9 different simulations created in this project. Instead of running each simulation individually, we will run a batch simulation using the run mode in GPX. From the simulation view, we will move on to the runs view to add a population simulation. From the Add dropdown, select Population Simulation, and we will use the propranolol simulation to run this population simulation. Hence, we will name our run as propranolol Pop Sim. Click Enter or click on OK. On the right-hand side, we will select the propranolol simulation by clicking on the Include toggle next to the propranolol simulation name. The simulation setting panel will be enabled. At the top of this panel is where you can specify the species, the ethnicity, the health status, the population size, repeated trial size, and population type. You can select PBPK from the population type if you have the PBPK model in your simulation. For this tutorial, we will leave everything as default. Species set to human, ethnicity set to American. We will have a healthy status, a population size of 25 subjects, and 1 repeated trial. As you can see, the population type is not enabled here because in our pharmacokinetic view for this particular simulation, we only have a compartmental model defined. We will now scroll down to the parameters table, wherein the default parameters are selected. The default coefficients of variation and distribution types are also shown. You can use the parameters list on the left-hand side, as shown here, to change the selection of variables by expanding the list as such, by clicking on the arrows and expanding the hierarchy tree, or using the search box, such as, for example, permeability. We can search perm and hit enter, so you can see that permeability is one of the included parameters to be varied in this population simulation. As you can see on the right-hand side, we have the CV% that you can also change if you'd like to by directly clicking on it in the table and changing it to the desired value. You can select the type of distribution you want for each variable, from log normal, uniform, or normal. In GPX, you also have this flexibility of adjusting the standard deviation, which is shown here as std_dev. For example, you could set the standard deviation to 1.2 as shown here for a coefficient variation of 20% for a log normal distribution. You also have the bounds factors displayed here. And the bounds factors defines the constraints for the lower and upper bounds. So for example, if the bounds factor is 3, which is the default value, that means that the lower and upper bound are 3 standard deviations. If you wish, you can also change this value. If you have made changes but would like to go back to the default values, you can do so by clicking on Set Default Parameters. And that will restore the selection and values to the default values. If you've created a particular population, you can save these settings by clicking on Save Population on the Save Population toggle, and then saving the project for this population to be saved in this particular run. We will now scroll down to the Run Controls panel because we're going to run a population simulation with all the default parameters selected. We will run to the control panels and click Start. You see that the Run Controls pop-up comes up showing the progression of the population simulation run. The Analysis view will automatically be activated when the run has completed. The population view mode is automatically selected for a population simulation and will display the CP time curve, which is the dark blue line, and the 9% confidence interval around it from the population simulation, which is the light blue band. The light blue band 9% confidence interval will get narrower as the number of subjects is increased. In the results sections, under the population view panel, click on the box next to percentiles. The percentiles that go from 10% to 100% will appear under the profile statistics. Hold the Control key on your keyboard and select the percentile 100% and drag your mouse down to select the other percentiles. The percentiles reflect the spread of the actual CP time profiles for the virtual population. The 100th percentile represents the highest concentration at each time point in the virtual population. From the population view, we will switch the mode to key view. The CP time profile for each individual is plotted. We can click across the key view ribbon to see the other plots, but of course they will be very busy since all the curves for each subject are plotted. While list on the CP time plot, we will expand the plot legend by clicking on the plus sign located at the top of the plot settings bar. This will enable us to see the plot legends. We will click on the simulation or on the curve with the highest Cmax on the graph, and the legend for this curve will be highlighted. Hover over the highlighted legend to see the full name with the trial and subject number. In this case, we can see that this particular curve is referring to subject 6. On the simulation list located to the left of the key view panel, we will unselect all the curves by clicking on the box next to trial 1. Once the selection has been cleared, we can select the subject that had the highest Cmax in this population, in which case was subject 6. We may need to drag the simulation list panel to the right to be able to see the full simulation name. We will now click on the box next to the subject 6 simulation. We can see now that all the plots here will be related to the subject 6, and you can do a more in-depth analysis of this particular subject. We will now switch the mode to summary view, and we'll reselect all the simulations by clicking on the square next to trial 1. Once all the subjects have been included again, we will drag this back to the left. And here in the summary view, we are able to compare the fraction absorbed, fraction to portal vein, and so on for each subject in this population. We will unselect the observed data on toggle to have a better visualization of the simulated profiles. You can sort each of these parameters by holding Alt on your keyboard and then clicking on the column header. As you can see here, subject 6 had the highest fraction absorbed. You can do so for each of these parameters. You can also examine the automatically generated output for a file that is saved in the population run project folder for more details on the individual variables values chosen during the simulation for each of these subsubjects. We will now run a virtual bioequivalence between two formulations that have different release profiles. As you can see, I have already set up a project for this exercise. Moving to the observed data view, we can see that a Weibull function has been fitted to the dissolution data for both the ER slow formulation and the ER slightly slow formulation. The Weibull function is shown here is represented by the red line and the observed data by the circles. Switching this to the slow formulation, we can see that a Weibull function has also been fitted to this dissolution data. Moving to the dosing view, we can see that the release for these two formulations is described by a Weibull parameter and not by tabulated data. And you can see this by selecting the formulation from the formulation dropdown and expanding the controlled release panel to see that the profile is set as distribution linked to the ER slow dissolution data. And if we switch to the slightly slow formulation, we can see that as well as the profile is described by the distribution, and that is linked to the slightly slow formulation. Going to the analysis view, you will see that I have previously run a simulation for each of these formulations, and you can see their simulated profile in the graph. Note that this plot has been formatted. As you can see, the slightly slow formulation, which is represented by the green, has a slightly higher exposure than the slow formulation. We will now assess if these formulations are bioequivalent. Navigating to the runs view, we can click on the add drop-down menu and select virtual bioequivalence from the drop-down. We will name our run slow versus slightly slow VBE. Moving to the right-hand side, we will click on the include toggle in front of the 500 mg ER slightly slow and 500 mg ER slow simulation names. That indicates that these simulations have been included in the VBE run. The simulation settings panel has now been enabled. We will select the ER slow formulation as our reference formulation from the reference formulation dropdown. And in this tutorial, we will run a crossover study, so we will leave the parallel study toggle unselected. We are also not going to assign any intra-subject variability, so we will leave these toggles unselected. And as you can imagine, this is also not a fed-fasted crossover, so we'll leave the toggle unselected. The Save Populations toggle is a function for you to save simulation settings that you might have created in this run. If you wish to save the population settings, you would click on this toggle and save the project to then be able to reuse the population settings. Switching the simulation to the reference simulation, we will set up a population that is human, American, healthy, 25 subjects, and 1 repeated trial. We will now scroll down to the parameters table, wherein the default parameters are selected. The default coefficients of variation and distribution types are also shown. You can use the parameters in the list on the left-hand side to change the selection of variables by expanding the list by clicking on the arrows, or simply by typing the variable that you wish to include in the search box. You can also note that the Weibull parameters are included in this have been automatically selected. The baseline values reflect the fitted values in the observed data view. We will now switch the simulation to the slightly slow simulation, and you can see that the population size and repeated trial have been grayed out. This is because this is not the reference simulation. We will now again scroll down to the parameters table and note that the Weibull scale and shape parameters now reflect the fitted values in the observed data view for this slightly slow formulation. When the test simulation is selected, in this case ER slightly slow, a crossover column appears in the parameter table. you might need to select the slider and drag it to the right to see the crossover column that has been added. The parameters that have the toggle on will have different sampled values between the two population simulations. And the parameters that have the toggle off will be the same in the test simulation as sampled in the reference population. We will save the project by clicking Save and then clicking on OK. We will use all the default parameters that are selected for a population simulation within the VBE run mode. We will now scroll down to the Run Controls panel and click on Start. The analysis view will automatically appear when the run has completed. The population view mode is automatically selected for a VBE run and will display the mean CP time curve and the 90% confidence interval for both slightly slow and slow formulations. We can expand the plot settings to have access to the plot legend, and we can select one of the mean curves to see which one that is related to. So hovering over the plot name, we can see that this is regarding the slightly slow formulation, and the lower one with the slower exposure, this is the ER slow formulation. We can switch the mode to the summary view, where you are able to see the fraction absorbed, the fraction into the portal vein, bioavailability, Cmax, Tmax, and so on for each subject in this population for each period, administration period. We will now open the automatically generated output file that is saved in the VBE project folder. You can see that our different files created here, and the iteration files are the populations that are created for each of these runs. And then the bioequivalence statistic is the Excel that we want to open to then be able to see the trial results. So here we can assess if the trial passed the 80 to 125% bioequivalence criteria. In terms of Cmax, the bioequivalence passed, the AUC as well. However, the AUC to infinity didn't pass, and the trial itself did not pass. Since this is a population simulation, your results might look slightly different than what's been presented in this video.